All right, let's have a look at the solution for this question. This is the solution to problem 2 from lecture 1, chapter 9. Problem states a steel bar of thickness H is welded to a vertical supporter shown in the below figure. What is the shear stress in the throat of the weld due to the force F equals 100 kilonewton? Take B as 50 millimeters, D as 30 millimeters, H as 5 millimeters. All right. So here we have our fillet weld, and the symbol shows that it's welded all the way around. All right. So this weld obviously means that this plate is sitting on top of the channel. So you're welding the side of this bar to the channel, the back of the bar to the channel, this side to the channel, and then underneath here. As you can see, the dotted line means that the bar is on top of the channel, so you have to weld on the underside. Let's look at the solution. So the solution simply is F equals the square root of 2, which is the same as this equation. The square root of 2 is 1.414. F of so square root 2 F divided by H times L. Our H is 5 millimeters, and our length is, what's the total length? It's going to be 2 times B plus 2 times D. Right? So that is the total length there. 2 times B plus 2 times D. Okay, and we calculate the shear stress. It's 177 MPa. That's the end of the solution to this question. Any questions?
Yes.
See, there's someone asked, where does the square root come from? As explained, the square root here, the square root of 2 is the same as 1.414. If you put the square root of 2 into a calculator, you get 1.414. So the solution is just writing it as square root F over HL instead of 1.414 F over HL. Hope that explains. Any other questions?
Why did you add D and B instead of multiplying them?
Well, why would you multiply B and D?
That's the formula.
No, it's not.
Length is not equal to B times D.
Length is equal to B plus D, which is multiplied by H. Let's go here again. Just explained it, but we'll explain it again. The length is equal to, so this is the equation you're looking at. All right, this equation is the same as this equation. Which is the same as this equation. Okay, we need the length. What is the length? Well, it's welded all the way around and underneath. Yeah. So what is the total length of this? What is my perimeter? That's what it is. The perimeter is the length. The length is going to equal to 2B plus 2D. So this is the same as writing it as this. That's my length. I plug it into this equation. What is it going to look like? Let's write it the way it looks like in the solution. It's not very complicated. It's very simple mathematics. Okay, that's the equation. Does that solve your problem? Do you understand now where it came from? Hello? Have I lost you? Do you understand now or not?
Yes, it's fine.
Okay. So remember, because you're welding on more sides, you're having more resistance. So that's why you've got to add it. You've got to add every side that makes up the length that's been welded, because the more sides that are welded, the more resistance to shear stress. You've got more area, because H times L is your area, is your throat area that's resisting. So the longer, the more weld you have, the longer the length of the weld, the more resistance. Okay, we're going to do one more problem for today, and then we're going to call it. All right, now we're getting into something. The first two questions I showed you are, you will never find a question like that in the exam. Those are too simple. You'll find something like this maybe in the exam, or something a bit more challenging. Not that it's difficult, but here we have a problem in torsion. All right, so it says here, a weld connection, as shown in the figure, is subject to a force F equals 7.5 kilonewton. Determine the size of the weld if the permissible shear stress for the weld is 100 MPa. Take D equals to 50 millimeters, B equal to 50 millimeters, and C equal to 100 millimeters. All right, now before we continue, I want to show you something, because I doubt any of you have actually watched the lectures on this. I have to show you if you want to know what is going on. Can everyone see the screen?
Yes, sir.
Yes, sir.
All right, so we have a problem like this. And this, what I'm going to explain to you now, sorry, this goes there. I'm going to explain to you now is vitally important. So this problem is welded here. Now, the equations for these problems are a bit more complex, and they are given in the tables. You're going to have two sets of tables you're going to be using to solve these type of problems. You're going to have table 9.1, which is for torsional properties. So please highlight that, because a lot of students confuse the two tables. You've got for torsional properties, and then you have for bending. You cannot use these interchangeably. The ones for bending are for bending problems, the one for torsion are for torsional problems. And then you get combined bending torsion problems, but we'll look at that later. All right, let's look at this table quickly first. You will see there is a line. Let me actually just bring this table. Before we continue, just want to go through this table quickly. I think it's important. I have to squash this table a bit. I like to work in PowerPoint instead of Word, instead of Paint, because it gives a clearer, it's easier to work with. All right, so what are we looking at here? Okay, we've got a number of equations. This is the throat area, which is very important in our equations for calculating shear stress. For instance, the primary shear stress will be equal to the shear force over the throat area A. Okay, so we need the throat area to calculate there. Then we have our center of gravities, the locations of our center of gravity, the coordinates, our x and y bar, and we have Ju, which is the unit polar moment of area. But I'll go through all of the stuff in the lectures. Quickly, just want to show you what these mean. I also go through them in the lectures, but just for your help here, I'm going to draw on this side. If we have a weld like this, okay, and it's on a bar, I'm just going to, it's on a, okay, let's just do it like that. So it's welded onto something like this. And you've got a welding sign here showing that it's welded just to one side. That means it's just welded there. Okay, this represents a line weld, just a line like this. It represents this here. Okay. So if I have a single weld like this, it's saying that I need to apply these equations, all right? This could also be a horizontal line. What's saying is if you only have one side welded, you must apply these equations. This says if we have two sides welded. So we have our bar and it's welded like this on the plate. We apply these equations. So it can be welded like this, or it could be welded, let me draw another one, because you can have it in two, it can be welded under the plate onto the channel, so welded there and there, so that will represent that. You've got your two lines. So if you have something like this or like this, you apply these equations. This is also two parts welded. What it's saying is that you have this side welded and this side, okay? So that would give you your sign would be something like this. And it would have another one here. Oh, sorry. Okay. Here we would have what? Three sides welded. So depending on what we have, we will select our equations. All right. So that's what these tables represent. That's what these shapes represent. Someone's mic is on. Mr. Forster, do you have a question?
No, sorry, Stas. Yeah, I accidentally activated it.
No problem. Okay, so I hope that makes sense. That is what these schematics are here that we see. They telling us how many sides are welded, and then if we know that, we then know which equations to apply. All right, so coming back here, we have a torsional problem. We have a force there F, and it's rotating about a center point. Okay. Now, when we solve these type of problems, generally what we solve for is we either trying to find how much force can be applied, so how much force here can be applied, or how thick the weld must be, okay? And what we're looking at is the point of greatest stress. So we're going to analyze the point of greatest stress. So where's the point of greatest stress here? Well, it's the point furthest away from the centroid, because we are having rotation about the center point. This force is causing that rotation. The furthest point from here is this point, or this point, or this point, or this point. The reason I'm saying that is because this is in the center. If we have a problem like this, we have a force and we have three welds. The center of gravity we're looking at here is not the center of this shape, it's the center of the weld. All right, the center of gravity of this weld, or the geometric center, we could say. So, for instance, if this weld is symmetric, the center of gravity is in the center. This weld is not symmetric, we have more weld mass on this side, which means my center of gravity is going to move closer to that side. All right, which means where's the furthest point from here? It's there, or there. And why is this important? Because we've got to calculate a value R like we did in chapter 8. And that is part of our equation. We're looking at the bending moment, the secondary stress. So once again here, like in chapter 8, we had a primary stress and we had a secondary stress. We're going to have that here in chapter 9. Okay. Now we're going to get two different types of problems. We're going to get a torsional problem and a bending problem. And it's vitally important that you are able to straight away identify if it's torsion or bending. I've had many students write the exam and they don't know the difference between a torsional problem and a bending problem. I give them a bending problem and they solve it like a torsional problem. Or I give them a torsional problem, they solve it using the equations for bending. And then the whole problem is wrong. So how do we know this is torsion? If we apply this force here, what are we going to get? We're going to get a twisting around the centroid. Okay, it's going to twist around the centroid. Now, just like chapter 8, we have two modes happening here. We have a translational mode, where we're considering this force acting directly at the centroid, plus, well, let me say plus, and that causes a primary shear force acting there. And then we also have our second mode, which is the rotation mode, which causes rotation. So once again, if we can imagine this in space, what's going to happen if I apply this force? It's going to move directly down as well as rotate. So there are two modes appearing. There's a translation and a rotation. All right, and this one gives us, if we're looking at this point, it gives us our primary, so that's this point here. And the moment gives us our secondary shear. Oh, sorry, let's rather write it as F, secondary shear. Okay, now we also get a bending problem. A bending problem will be, I'm going to draw it here. Just excuse me, I'm going to try my best. So it's welded onto some plate, and there's a force here. The center of gravity, or should I say the center of this point, is there. With this type of problem, we do not get rotation. We do not get rotation about or twisting about the center. We get bending. It bends about the center, it doesn't rotate. All right, so that's how we identify. Do we have twisting? If we have twisting about the center, then it is a torsional problem. Is there any twisting here? No, it's bending. I'm getting a tensile and a compressive stress there. It's a bending problem. So that means I apply the bending equations. Okay. And then we do get a combined problem, but we'll tackle that later on. I want to get to solving the question. So what you guys are going to then look at is, okay, we've got weld here. It's a torsional problem because we are twisting about the center. So you need to go to the table 9-1, apply those equations and try to solve. I'm going to give you guys some time to try analyze this, and then we'll look at the solution. If you have any questions, please feel free to ask. Any questions?
Sir,
Yes.
given a question like this, but the welds were on all four sides, would it still be a torsional problem?
Yes. All problems like this are torsional. Like I said, if you get twisting about the centroid, it's torsional.
Okay, no problem.
If there's
sir.
no,
Thank
if
you.
there's no twisting, then it's bending.
Regardless of whether the force is pulling from the inside or pushing from the top.
Like I said, if it's twisting, it's torsional. It's bending. We'll have a look at some bending problems as we go, and you'll start being able to identify which is torsional, which is bending.
Okay, no problem, sir. Thank you.
Right, I think let's have a look at the solution, because we are running out of time. So I'm going to start recording and record the problem, and then we'll look at the solution. So I'm going to start that again. I don't want my emails popping up and recording. Hi, this is a solution to problem 3, chapter 9, lecture 1. Problem states a weld connection is shown in the figure subject to a force of F equals 7.5 kilonewtons. Determine the size of the weld if the permissible shear stress for the weld is 100 MPa. Take D as 50 millimeters, so that's the depth, B is 50, and C as 100. All right. W1 is referring to weld 1, W2 is referring to weld 2, and we have a weld on both sides as indicated by the symbol. We also have offset or eccentric force, which is at a distance from the centroid, causing a rotation by the centroid. So this is a torsional problem. Let's have a look at the solution. All right, so what we can calculate first. Firstly, we're going to go to table, let's just quickly go to table. We're going to go to table 9-1. It has two welds, so we'll use the equations here from point 2 and apply them to the problem. Okay, so we can calculate the center of gravity, or the centroids, x bar and y bar, which is just b over 2 and d over 2, 25, 25. We can calculate the unit polar moment of area, which gives me 83,333 millimeters cubed. My distance r from the centroid, as we can from here, our problem is going to look like this. Our distance r to the point of greatest shear stress. This is where my primary shear stress is going to be, and my secondary shear stress. This point r is at a distance y bar and x bar. Sorry, Actually, we always take, this is x bar here, and this distance here is going to be, this is my length b. So this distance here is going to be b minus x bar. Okay, that's that distance there. That's important to note. All right, so we've got that distance, b minus x bar squared plus y bar squared. That gives me 35.355 millimeters. My angle, so if we look at our angle, theta, where do we calculate the angle theta? So if I'm looking at this angle here, this angle is going to be opposite over hypotenuse, so theta will be opposite b minus x bar. Tan theta will be b minus x over y bar. Now you can either calculate this angle or this angle here. If we calculate this angle is going to be the same as, if I'm not mistaken, this angle here. Okay. Just have to double check me there. Because this angle here, let's call this alpha. This is the same as this angle there. All right, so we get theta equals 10, b minus x bar over y bar, gives me 45 degrees. Calculate my weld area or throat area, which is 70.7 times h, because we don't have h, we're looking for h. Our second polar moment is going to be, we can solve here, which is going to be 58,916.667 multiplied by h. So it's going to be all in terms of h because we need to solve for h. Then my primary shear is going to be tau prime is equal to f over a. That's going to equal then the force we have, but the area we don't because we need h. So we're going to be in terms of this. Our secondary shear for from our moment is mr over j, and that's going to be then 562,584 times 1 over 8 h. We can break that into two components because we have our secondary shear here. So if we have our secondary shear with this angle, we're going to break it into these two, why is it doing that? Okay, so I'm going to break into those two components opposite. So this is tau double prime sine theta, and tau double prime cos theta. Right. Okay, so that's where we get those two components, tau x double prime and tau y double prime. Now solving for our maximum shear, just like we looked at the equations in chapter 8, we're going to have our horizontal components squared plus our vertical components squared, and we can solve for that. Then once you plug everything, we make h a subject of the formula. Well, we can find the maximum shear and then plug it into this equation and solve for h, which will give us 6.419 millimeters. That's the end of the solution for this problem. All right, any questions? I'm guessing most of you are going, what was that? Or were you able to follow?
I was sort of able to follow.
All right, if you're sort of able to follow, that's a good thing. What I'm going to do, I am going to upload, look, these questions are quite similar to the cantilever questions in chapter 8. Obviously, some of the formulas are different, but the approach is very similar. I'm going to upload these solutions we've done, and this particular solution we just have done now. I want you guys to go through the solution slowly, but I want you to solve the problem while you're going through the solution. All right, so try solve the problem and then refer to the solution as you go through it, and then you will start making sense of it. Also, it is a bit difficult because you guys haven't started the work for chapter 9, which you would have supposed to have already done that. But we are going to work through a lot of these problems. So by the end of the chapter, basically, this is the hardest kind of problem. The problems don't really get harder than this. Okay, what we've looked at today is pretty much the rest of the chapter. So this is a really, once you get the concept here, it's really easy and it's 3 points. Normally most students score almost 100% or 100% for this problem in the exam because it is a straightforward question. Once you know what to do and you can identify them, the only place students really struggle is identifying, or should I say, when students fail this problem is only because they've identified it wrong. They've either identified it as a bending problem when it's a torsional problem, or a torsional problem when it's a bending problem. All right, but this is how the hardest it gets for this chapter. If you're able to solve these problems, then the chapter is straightforward from here on. All right, so please go through the problem we just done now, and it will prepare you then for the rest of the lectures. Also, start going through the lectures so you do not fall behind. Any questions?
All good from our side.
All right, if you guys are happy, you can leave. We are finished the class for today.